Hello friends, if you're watching my video for the first time, please subscribe my channel. Your support will really encourage me to upload video like this for you. Hello friends, in this video we'll learn how to build a TCSC compensated transmission line in PSCAD. First I will give some basic idea about TCSC. TCSC means thyristor control series capacitor, which is nothing but a series connected flexible AC transmission system device. Here we have listed some previous installation of TCSC. TCSC is first commissioned in 1991 by American Electric Power Company in USA. After that, and in 1992, Western Area Power Administration installed a three-phase TCAC module at 230 kV substation in Arizona. In 1993, the General Electric and EPRI collaboratively commissioned a project for a three-phase TCAC at 500 kV substation. In Sweden, 400 kV transmission line is compensated by a TCAC, where TCAC and fixed capacitor combinedly connected. In India, first TCAC is commissioned by PGCIL, that is Power Grid Corporation India Limited, in Kanpur Vallabhgarh transmission line. India's second TCAC project was commissioned by PGCIL as well, between Roadkill and Raipur transmission line of capacity 9,000 megawatt, and it is double circuited transmission line 412 kilometer. Okay, this is the basic previous installation, and now I'm going to the design aspect. TCAC is nothing but a fixed series capacitor connected in parallel with a thyristor control reactor of inductance L. You can see that this is the TCR, where inductor and anti-parallel thyristor switch is connected, right? So this combination is called a basic TCAC, and this MOB means metal oxide varistor, is used to provide over voltage protection of this capacitor during fault. So if we calculate the overall impedance across the TCAC, first just remove the MOV, then if we calculate this impedance, this TCAC, we consider this TCAC for calculation of impedance, then we will get this impedance as XTCAC as XC minus XC square by XC minus XL, where XC is the reactive impedance of XC and XL is reactive impedance of L, right? Plus into 2i's beta plus 2 sine 2i's beta divided by pi, where beta is pi minus alpha and alpha is the firing angle of the thyristor T1. So firing angle of the thyristor T2 will be pi plus alpha, right? Because this is anti-parallel and 180 degree out of phase. And plus 4xc square divided by xc minus xl into cos square beta divided by k minus 1, where k equals to root over of xc by xl into k tan k beta minus tan beta by pi. Now if we plot this XTCSC, say per unit value, take per unit value means XTCSC divided by XC. Okay, so take common from this, all these terms, take common XC from all these terms and divided by just XTCSC divided by XC. This will give you the per unit XTCSC, right? And versus alpha, right? Alpha of the TCSC can be varied from 90 degree to 180 degree. In this plot, it is shown at from 100 degree to 180 degree, but you can find in the book. I should give the reference. You can go through the book by Mathur. Okay, the fax device book by Mathur. This is a very good book, and if we find that the TCSU will operate at firing angle from 90 degree to 180 degree. So now if we plot the values, whatever the values of XE and XL, we will get the um, this characteristics, impedance characteristics, like this, from 90 degree to somewhere 138 degree to 140 degree. The TCSC will behaves like an inductor, right? And the impedance of the TCSC will increase. Means TCSC will provide the inductive reactance, you can say, to the transmission line. So overall inductance of the transmission line will increase. Now if we means if alpha is varied from say 140 degree to 180 degree, the TCSC will operate in capacitive zone, right? So capacitive zone, in this region, the net impedance of the transmission line will decrease, because X line minus XC will be there, so net impedance will be decreased. Now one important thing is there, between say 138 degree to 140 degree, you can see that this is nothing but a resonance region where XC becomes XL. So we have to avoid this zone to avoid overcompensation. So we need to take say 90 degree to 130 degree for inductive operation, and 145 to or 150 degree to 180 degree for capacitive operation. Okay, now for modeling purpose, we are selecting this system, where this is a 2 machine 2 bus system, where bus 1 voltage is V at angle delta, and bus 2 voltage is also V, but angle is 0 degree. So power flow from bus 1 to bus 2, right? Now TCSC is placed just near the bus 1, and this is the transmission line of impedance X line, right? Now we need to calculate this C value, L value, and MOV, voltage across MOV. So what we will do, we need this calculation can be found in Mathur's book as well, and in few research papers you can see this kinds of calculation. So if we need to compensate the line impedance, say 30% of the transmission line, or 30% of the impedance is need to be compensated. So our XE will be, XE means in a capacitive impedance of this C, so XE will be 30% of X line. Okay, so if we calculate this, X line is known to us. Okay, so if it is calculated by this formula, we will get this XC. Now C can be found by this formula, and this is a well-known formula. I don't need to elaborate these things. You will get the value of C. Now it is a convention that the XL, this L means this impedance across this L will be 15 to 30% of XC. So take any value from 15 to 30%. Okay, so 15 to 30% of XC is known from this formula. Then we can find the XL, and L can be found from this formula. This is as well, means this is well known formula as well. So we'll get the value of C and L. Now the voltage across MOV we need to calculate. So MOV, what the operation of MOV will provide the over voltage protection of capacitor during fault. So if there is a fault in the transmission line, say very near to the TCSC, okay, so fault current will be very high. Okay, no fault current, if fault current is very high, the voltage across the capacitor will also increase. Measure this voltage across capacitor during fault condition. Okay, so multiply it with 2 to 2.5. No, sorry, this is during normal condition, this is not fault condition. Normal condition. Okay, right. Now whatever the voltage across capacitor in normal condition, just multiply it by 2.5 times. It will give you the voltage across MOV. So voltage across MOV we need to select from this formula. When a fault occur, the capacitor voltage will increase VC. Whatever the voltage across capacitor will increase, it may damage the capacitor, so we need to protect by MOV. So MOV means suppose the voltage across capacitor say 25 kV in normal condition. So take 2 as multiplying constant, so voltage across MOV will be 50. Okay, 50 kV. So a fault occurs, then after 50 kV, after 50 kV the capacitor, the voltage of the across capacitor will increase up to 50 kV, or means 3-phase voltage we need to multiply root 3 by whatever the constant, you know that the voltage across capacitor will will not cross the limit, will not cross the voltage across MOV, because after a certain voltage of the capacitor the MOV will start operating. Means in normal condition MOV impedance, MOV is a non-linear resistor, you can say. Non-linear resistor in normal condition the current is means voltage is very low across the capacitor, so it will not operate. It will provide a high, very high, infinite impedance, you can say. Infinite impedance in MOV, so the current will not flow through MOV. But when fault occur, the voltage across capacitor increase. Now voltage across capacitor means voltage across MOV, because there is no other components is there in MOV circuit. So voltage across MOV, say it cross voltage set value, whatever VMOV is there. After VMOV, this MOV will start operating. So some of the current will obviously flow through the capacitor, but maximum current will flow through MOV. As in this condition the MOV behaves like a short circuit. Okay, the impedance is very low, so maximum current will flow through MOV. So this is the basic principle of MOV. You can go through about MOV from Google it. Okay, whatever the thing you can get from research, various research paper as well. So this is nothing but the basic design aspect of this modeling. Now I am going to the PSCAD modeling. So this is a PSCAD modeling where the same model is taken, where two machine two bus system. This is a voltage source 1, where voltage across means voltage source is 400 kV, and phase shift is taken 10 degree, means delta equals to 10, and for this source 2, this is 400 kV, and this is 0 degree. Okay, now transmission line, and this two machine two bus system I have made a video earlier. So okay, I will give the link in the description box. You can see that. You will find in those videos the modeling of means transmission line. So we will get the positive sequence and zero sequence impedance of the transmission line. Now if we see that this is 224 kilometer transmission line, and this is 96, so 224 plus 96 is nothing but 320 kilometer. Okay, so this is 320 kilometer transmission line, and if we need to create a fault, we need to split up the transmission line and connect this fault block in between these two transmission line. Okay, so 224 kilometer means 224 divided by 320, that is equals to 70%. Yes, 70%. At 70% location from bus 1, we are creating a three-phase fault, as written here, ABC, three-phase fault. As it is a short circuit fault, the fault resistance I have taken 1, and this fault resistance for a short circuit fault is negligibly small, but okay, 1 ohm can be given, because 1 ohm for a 400 kV transmission line is very much negligible, and we are creating a fault at 1 second, and duration of faults, say, take 1 second as well. Okay, now this is the TCSC module, right? So in the block we will find the actual module. So how to create a means custom block, I have made a video earlier, so I will give the link in the description box as well. Okay, this is the TCSC, and now I have to find the XC, means C and L, right? Okay, now take means go back. Now we can see that the positive sequence impedance, take reactance positive, because R is very less for a transmission line. For a well conditioned transmission line, XL by means XL by R will be very large, so we can neglect R. So take XL equals to 0.3674 e to the means 10 to the power minus 3 ohm per meter, means 0.3674 ohm per kilometer, right? So okay, 0.3674, so X line will be 0.3674 into 320 kilometer. It will give the total line impedance, and if we need to compensate 30%, we need to multiply it by 0.3, and we get the XC, and we get the C from this formula. And if we get the XC, we will calculate the XL as well. Take any value from 15% to 30% and get the XL, means L. Okay, so we have taken the C value is 101.4 microfarad, and L equals to 0.015 hertz by this formula. Okay, we have calculated earlier. Now this is a three-phase TCR, right? And this are the anti-parallel thyristor for phase A, B, C, and the firing pulse are given AP1, AP2, AP3, AP4, AP5, AP6, whatever. Okay, now capacitor is here. Now this firing pulse we have to build a means firing pulse generator circuit. So how we will build? Now what the control mechanism, it is seen, it can be seen from the book as well. Now I'm just mentioning this. Take the voltage across this TCR. Say this is your phase A, right? So this voltage will give your voltage across TCR for phase A. This is for phase B, this is for phase C. Okay, now connect a PLL module. Okay, PLL module, phase lock loop. This block is whatever this block uh, do, you can find from the help. This component is a 3-phase PI control phase lock loop, where it generates ramp signal theta that varies from 0 to 160 degree. And this is very important, synchronized or locked in phase with VA. So whatever will give in VA, the phase of this theta will maintaining the phase with VA and VB. If we don't connect VBA and VC, obviously we need to connect something, but this will not matter for theta phase of the theta. So theta will maintain the phase of VA, right? So we have to generate a ramp signal from phase A. So we need to provide this EA as input, okay, and take VB and VC as 0, right? And now we will get the PLL1 output, where we get the ramp signal maintaining the phase of EA. Like that we will get the PLL2 and PLL3 for the phase B and phase C respectively, right? Now this HL high low, this is nothing but a firing pulse generator, right? This can be thyristor based, this can be also GTO based. So this is thyristor we have taken for this anti-parallel switch, so we have to select this thyristor. Okay, now whatever the means actually this means this is a comparator circuit, you can say. Means PL and this high greater than low, then firing pulse will be 1. High less than low, firing pulse will be 0. This kind of thing. Okay, now we get we provide the input PLL1 from this to high and low to low. We need to connect a firing pulse. This is 160 degree what I have given. This is nothing but the firing pulse of the thyristor switch. So if we just take edit the dimension, this is nothing but C and dimension is 1. This is the input data, right? Now how to go back? Okay, now this is the C, the firing pulse. Okay, it is compared with the PLL1. For PLL1 is compared with the firing angle. This is for firing angle 1, right? And firing angle 2 will be same but 180 degree out of phase. So we need to add this 180 degree with the firing pulse C. Okay, whatever the firing pulse will come here, we will add 180 degree. This angle will compared with the PLL1 and we get the firing pulse AP2. Likewise for the phase B and phase C, we can see the same principle is maintained. Okay, now for MOV, where we found in the master library, go to passive element, we will found the you will find the metal oxide charger. This is nothing but a MOV. So just okay, at first just take okay, first see the firing pulse, whatever firing pulse is happening, we need to see. Take this as 3 seconds. At 3 seconds the fault will start, right? Now we need to see the PLL1. Now this is your alpha, say 1, alpha 1, actually it is alpha. Okay, okay, display it and just copy it and paste it here. This is your alpha 2. Alpha 2 means alpha 1 plus 180 degree, right? And just take this AP1, copy it, paste it here, connect here as AP2, right? Now just take a plot, add a overlay graph. Okay, first just delete it first. At right click, we need to see the firing pulse, so it will it must be digital, right? 0 1. So I need to connect this to digital plot. Okay, now we are comparing this PLL1 and alpha 1. So first take alpha 1, just click on the alpha 1, press your control key from the keyboard and drag it here. For PLL1, just drag it here as, and this is your alpha 2. Okay, now you will get the firing pulse 1 here and firing pulse 2 here, right? Okay, save it first. Okay, just run it. Okay, make it digital. Okay, now you can see that if I just zoom in a portion, this is nothing but this PLL green plot will be the PLL output, right? PLL output means ramp signal, and it varies between 0 to 360 degree, right? And just alpha 1, what we have given 160 degree. So this red one is your alpha 1, 160 degree plus 180 degree, 160 degree plus 180 degree, how much? 340 degree. So this blue line will be your alpha 2. So this is 140 degree. Now just comparing alpha 1 and PLL1, right? Just comparing alpha 1 and PLL1. PLL1 greater than alpha 1, then we get a firing pulse, and we width of the firing pulse you can just mention from here as well. Pulse duration in time we can mention. Okay, this width of the firing pulse can be changed by this. Okay, now PLL1 greater than AP1 will give you the firing pulse 0 to 1. Okay. Oh, just double click on this. Okay, this is nothing 0, this is nothing but 0, this is 1, and this is a digital plot. So means PLL1 greater than alpha 1, this will give you the AP1 positive, means plus 1, otherwise it will 0, means in this condition you have take PLL1 less than alpha 1, this will give 0 output. Now PLL1 is compared with alpha 2 greater than 1, this will give you 1 output, less than 1, this will give you the 0 output. So it is understood from this plot that our control circuit of the thyristor means parallel thyristor is working fine, right? Now what we need to take the voltage across capacitor at first. So voltage across capacitor V underscore C have taken, so we need to write V underscore C. Okay, now connect this V underscore C, display it. Okay, now connect overlay graph and now run it again. So this is nothing but a 3 phase. So this is almost 25 kV you can see from this plot. Okay, 24 we take 25. So means this VC will be 25, so VMOV will be 2 into 25. Take 2 into 25. Okay, so what I need to do, go to master library, take metal oxide varistor, copy it and paste it here, just rotate it and connect it in between this, double click it, and this arrestor voltage rating will take 50. Okay, now we have to see some of the plots. Take VC, IC, okay. Now as this is a 3-phase plot, so what we need to do, we just need to see the first plot, that is your VCA, A phase. Okay, and capacitor current ICA current. Okay, and for MOV just copy it and paste it and write this I underscore MOV. So this will be I underscore MOV. So this will be I underscore MOV. Oh, MOV A, right? Okay, now take 2 more plots. Now this will be capacitive current, this is your MOV current. Now run it again. Okay, we can see that at 3 second we are creating a 3 phase fault, right? Okay, take 150 for better visibility. Say to 5 minus 5, and take here 5 minus 5. Okay, we can see that in normal condition, when there is no fault, the whole current is flowing through the capacitor. Means not whole current, no whole line current, some through the capacitor, some through the inductor as well. So okay, take inductor voltage and current as well. Now we can see that this VL and IL is connected in phase this circuit, so we don't need to give this data tab, we can directly connect through it. And this is VL, this is actually equals to VLA, and I need to delete it first. IL, this is actually ILA. So connect to more graph. Right, now run it again. Now you can see that in normal conditions some of the line current is flowing through the capacitor, some of the line current will flow through the inductor. There is no current is flowing through MOV, but when a fault occur and it the voltage across capacitor just cross the voltage rating of MOV, the MOV start operating, right? If we see that the MOV current is like this, and the voltage across capacitor some is little flat top, you can say, and part of the capacitive current is flowing through this MOV. So just if we means take this thing, you can see that it is nothing but if we just consider the superimposed of capacitive current and capacitor current and MOV current, this is nothing but a sinusoid. Okay, but when we create a fault, some part of the line current is flowing through MOV and some part is flowing through the capacitor. So this is the inductive voltage and inductive current, and this voltage across capacitor is little like flat top, you can say. Up to some certain voltage across capacitor, this will not exceed. during fault condition. Whatever we have given in the MOV reference voltage, this will not cross the voltage across MOV, means actually the voltage across capacitor, because there is no other components is connected with the MOV. So greater than 50 means 50 is 50 into whatever to make it three phase. This is the voltage, and beyond this voltage the capacitor will not will not cross this voltage to avoid damage, right? So this is the operating of TCSC. So I will give this model in the description box. You can go through it. First you need to go through the Mathur's book. It will give you a clear understanding about the TCSC, and if you see this video, I hope you will get a clear picture on TCSC. Okay, this is the end of this video, and don't forget to subscribe my channel. Your support is needed. So thank you.